Now we have our next speaker, Andre Noguria Souza. He is a senior HPC engineer and AI scientist at Rescale and a visiting scientist at MIT, working at the intersection of high-performance computing, applied mathematics, and machine learning for engineering and physics applications. His research interests include generative and physics-informed machine learning, stochastic processes, and scalable numerical methods with a particular emphasis on data-driven emulation. I welcome Andre.
All right, let's see if I can get this thing working here. Okay, entire screen. Okay, wonderful. All right, good morning, everyone. So I'll be talking a little bit about how we can begin building models and AI methods that give us insights that we couldn't necessarily have had before. And I'll go in detail about what I mean by this. This is a project that grew out of work that I did at MIT with several collaborators at MIT, including Simone, who just spoke. So just to give a recap of some of the stuff that we've seen in the conference thus far, we've seen satellites, so ways of making observations of our Earth system, usually on the surface or some integrated quantity along the surface to the satellite. We've seen ocean stuff, either by just staring outside or by looking at Simone's simulations. And we've seen lots of different kinds of models for representing, well, physical processes that we care about or mathematical models we care about. And we've seen various ways of combining models with data, and the SciML ecosystem that Chris has is a good example of how we combine these things together. And for this talk, I'm going to discuss yet another way that we can take data and models and do stuff with it. So the way that I'm going to describe in this talk of this combination is predicated on, let's say, a very classic approach coming from any kind of physical theory, where the goal of a physical theory, in my mind, is to make inferences with less data, whether it's to predict what happens in the future with what we can measure now. So that's an inference for the future, something we haven't observed yet. Or perhaps we only have partial information of a system. Like for Maxwell's equations, one of the great successes is that you can only measure along a boundary of something and be able to infer what happens within the volume. So it's much less information that you need to actually make a prediction about what's happening. And physical theories let us bridge that gap between what's observed and what we don't observe and make sensible predictions. But for complex systems such as the atmosphere, the ocean, or in general any kind of chaotic systems, the best that we can do is having a numerical model to represent what the system does. And because of computational irreducibility, we can't just represent it as just some simple function of, let's say, an inverse Laplacian or multiplying by some number in order to say, hey, this is how we make an inference. We have to evolve things forward and see what happens. So then we can go to the next step, where with computational models and data-driven approaches, we can kind of expand this theory plus data paradigm that has existed in physics, but use more complex models. And specifically, I'm going to focus on the inferences part for this beginning part of the talk a little bit about a philosophy of what we mean by inference. And then I'll move on to the specific ocean application afterwards. So as scientists or engineers, we often ask some question about information we have and some inference that we want. So here X represents any kind of information that we have. For this talk, it'll be information about the ocean surface, and Y, the information we want, will be the ocean interior, meaning currents in the underneath the ocean, in the interior, the temperature, the salinity profile, density, etc. And then we have some way of making an inference, this function f. And this function f can be an ODE solver that takes some initial conditions and outputs some final condition. It can be Newton's laws of motion. It can be the Navier-Stokes equation, whatever we want. But the goal here, the point is that it's a deterministic case. Like every single time that we plug in a given piece of information, we only get one thing out. That's the definition of a function. More often than not in science, that's actually not what we want. We don't want just some deterministic answer like we plug in one value, we get exactly another value out. What we really want is more of a probabilistic inference, where here it's very much the same kind of question, where we have some given information that's again represented by x, some information that we want y, but the way that the inference works is that we draw from a distribution. So you ask for a given piece of information and you don't know exactly what it is. You get a range of values of what's possible instead. And there is a connection between this functional form and the probabilistic version, in that the probabilistic version is a generalization of the former. So if we had perfect information and it's perfectly predictive, then this probability distribution, here represented by rho, so not a density, a probability density, then this is just a delta function centered on y minus f of x. So the probabilistic formulation generalizes the other one. Again, just drawing a single sample and only getting a single answer at a time, that's a delta function. So this works really well for cases where functional forms between quantities you care about exist. So here I'm looking at the function y equals x squared as an example. You plug in x equals 2, you always get y equals 4. You plug in x equals negative 2, you also get y equals 4, etc. Plus or minus doesn't matter here. Now, when this starts making a difference is when you start wanting to go backwards. So instead of asking, okay, given y, what could have x been? So let's go through a thought process here. If y is 4, there's two values that x could have been. It could have been minus 2 or plus 2. There isn't a functional form that just gets us from that value to 2. It's two possibilities. The probabilistic formulation allows us to get around that by saying like, okay, maybe I don't know if it's the plus or the minus, but I can say that it's 50% of the time the plus or 50% of the time the minus. So that kind of branch selection process isn't necessary with a probabilistic formulation. You can kind of hedge your bets, say, okay, it's one or the other. Now, why is this important for machine learning? And how does this apply to what I'm going to discuss down the line with the ocean inference? Is that I'd say most problems in science are this kind of ill-posed nature where a given answer isn't actually perfectly informative of what you want to find. And secondly, let's say you train a machine learning model to find the square root, but you have the plus or minus branch. And you do this whole training procedure. And half the time, the neural network sees like, oh, the square root of 4 is 2, and half the time it sees it's minus 2. If you train a neural network on this, it's always going to produce, eventually the minimizer of that is going to be 0. So if you ask a neural network what the square root of 4 is, it's going to tell you 0. The square root of 9, it'll tell you 0, etc. That's what the training procedure would give you. Whereas with, let's say, generative AI methods, it won't do that. It'll produce plus 2 or minus 2 half the time. So that's the benefit of using something like generative AI already, even from this simple example. So the other benefit of using this probabilistic formulation is that you can do uncertainty quantification. You can figure out, is the given amount of information that I've supplied informative enough of what I want to predict? So that's kind of the functional form situation. That's when you have useful information. The information that you provide to model is actually useful for making an inference. But in the case that your information is completely useless, that input does not affect the output at all, then a probabilistic formulation reduces to the marginal density in this case. And we'll see examples of what I mean by this shortly. So no matter what happens, you still get something informative. And as long as the generative model is somewhat constrained by the input that you have, then you've been doing something, let's say, useful on a scientific level. So basically the former problem is a bit ill-posed when it comes to just a scientific question because a functional form just may not exist. whereas the latter is always well posed. Even if there isn't an exact relationship, you'll be able to say something. There is a relationship between the two in terms of machine learning, in that if you train a method to try to find just a deterministic function and it's an L2 loss, then the connection is that line on the bottom, that the function that you'll find is actually the expected value of your conditional distribution. So that's the functional form that a neural network would find, let's say if you do L2 training. So the big difference between what we can do now that we couldn't do before, and it's thanks to this revolution in, both compute, algorithms, and let's say just general approaches of practical engineering to make these systems work, is that both the Y and the X can be high dimensional. And what I mean by high dimensional is that they can be images. So you can take one image and you can predict another image. And because it can be this high dimensional object, we can ask, much more sophisticated kind of scientific questions. And the method that I'm going to use to let's say, characterize this conditional distribution is a score-based diffusion model, but you can use other methods as well, like flow matching is a good example of other methods. But there is a reason why I like score-based diffusion models specifically, and it's that you also get the score function out of it. And I'll end the tutorial in the afternoon. We'll see exactly what that is. But that object helps you compute many other things as well. So you get for free this extra little function that you can play around with and do more things with. The neural network architecture, personally, I don't think matters too much, as long as you include the right kind of inductive bias. And here I'm using a modified unit to take into account the diffusion process. So to recap, X, information that we want, X, information that we have, Y, information that we want. In this case, this X will be the ocean surface, because that's essentially what we measure with satellites. And what we'll want to predict is the ocean interior. And the thing that'll bridge the gap between being able to make what we observe with what we don't observe is going to be an ocean model. And this ocean model I will treat as a perfect model in order for making this inference. So I assume that it is the best, most calibrated, most well-designed ocean model, aka oceananigans. And it'll do the best job that we can to make an inference of the ocean interior. So in pictures, what we have is satellite measurements of the surface. But really what we want is to put measurements inside the ocean and be able to figure out what's going on. There are actual measurements in the interior of the ocean as well, but I'm going to ignore that for now. So specifically for this ocean inference question, I'm going to take a 3D Navier-Stokes equation, and it's going to have this many degrees of freedom. So it's a three-dimensional simulation. And the important part is that it has the representation of the sea surface height, or the free surface height, as I'm calling it here. And that's something that can ostensibly be measured by satellites. And the predicted information, the thing that we have less information on, is going to be the 3D interior ocean state. And this inference will be drawn from the ocean model itself. So the ocean model has an idea of free surface height. It also has an idea of what the 3D ocean interior looks like. And the game that we're going to play is, if I know the free surface height, I can predict the interior. So eventually we'd be able to just take a satellite measurement and predict the ocean interior from that. That's the downstream application, but here everything is going to be more idealized. And here I'm showing some images so that I can be very specific about what we're predicting. So the images on the left, the first column, that's a visual representation of the free surface height. And for those in the know, for oceanographers, this is a double gyre simulation, but in a very highly nonlinear regime. So that's the given information, is that image. And what we'd like to do is predict, in this case, the other 4 images, but it's actually 60 other images that's being predicted by the model. These 4 images are at a 400-meter depth of the ocean. If you take a slice, it's predicting the horizontal velocity, so that's the east-west velocity. That's the first image. The second image is the north-south velocity. The third, up-down velocity. And the last one, the temperature field. But you can actually even ignore the physics, because once you go into machine learning land, it's just given that image, predict the other images. And that's the kind of thing that you can do nowadays that you couldn't do before. Also, just for the oceanographers, there's in this simulation, I have convection in it as well. So it's not exactly a very traditional double gyre simulation. And to make sure that I'm not doing, let's say, cheating in my examples that I'm going to show you, I'm dividing the training data set in a very particular way where when I start the simulation, I discard the first 100 years of the simulation. I train on the next 200 years. And then all the evaluations that I'm showing you are on the last 50 years of the simulation, which are 50 years in the future from the last training point of the simulation. So I can be guaranteed that the data that I'm going to present the neural network model is completely decorrelated and independent from all the things that it's seen before. 50 years in the future. Yeah, and that's what the blue, red, and orange regimes represent here. So just showing some results now of what happens when you try to do this inference problem. Again, the given piece of information is that image. And the goal, predict the ocean subsurface state at several different depths. And later on, we'll see what happens when we lose information as well on the sea surface height. So because this is 50 years in the future, and I do have an ocean simulation that saw this sea surface height, the ocean simulation itself produced that image that we see there. And I trained a neural network, again, over that 250-year time period. This is 50 years in the future that I'm going to draw this inference from. One sample of the neural network, remember, this is no longer a deterministic function anymore. When I give it a free surface height, it's going to generate many plausible states for the, in this case, the east-west velocity. But this is one of them. And just looking at the two, by eye, they look pretty similar, but there are actual differences, and I'll show that in a second. But if I draw another sample, it looks like this. And if I take the ensemble mean of the 100 samples that I drew, it looks like that image over there under AI mean. So you see that the AI means and AI samples all look very similar to the ocean simulation itself. And so if I take the difference between the ocean simulation and the AI mean, you see that there are actually some small differences, and that's the yellow region on the image where everything's lit up. And physically, this makes sense too. This is where there's the most amount of chaos and eddy variability. So specifically where you have the meander and the double gyre, and where you have convection in the north of the simulation. So it corresponds to the physics that we know. We don't think we can actually pin down the predictions perfectly in those kind of regions. And the model is saying like, well, yeah, the ensemble mean is actually it isn't as close as it could be to the data that we're observing. But again, I have 100 samples that I drew. And I can also look at the standard deviation of those 100 samples. And so the standard deviation of the 100 samples actually looks a lot like the difference between the ensemble mean and the actual ocean simulation. In other words, the machine learning model knows that it's uncertain exactly on the regions that it's different from the ensemble mean. Stated differently, the machine learning method can tell you when you're uncertain about making a prediction. And that's one of the benefits of using a generative method, that you get that kind of a priori error estimate of like, yeah, I don't think you can make a prediction here, at least based off of how things were trained. You can do this for other components too. This is the at the north-south velocity, and it's a very similar story. For convection, also a similar story. Here you see much more unpredictability in the north of the domain. So that's the yellow region at the top of the image. And again, that's just because we're measuring this free surface height, and it's difficult to, with just that piece of information, to decide whether at a very high or at a 400 meter depth, whether things are going up or down. And the temperature field, which is very well predicted since it doesn't have much variability. One other thing to notice, especially about the vertical velocity field, so that's the third row, is that the ensemble mean, you'll see just by eye, there seems to be a little bit more white in the top of it. And that's because a lot of the up-down fluctuations are canceling out to give you essentially saying like, okay, I'm predicting 0. This is very much like that square root problem that we saw before with the plus minus square root. You can't decide whether it's going up or down. So on average, it's just going to predict 0 if you take the ensemble mean. Another point that I like to make, that ensemble mean, AI mean column, is what you'd get if you just trained a regular machine learning model to do the prediction. So you get the regular machine learning inference question with a L2 for free when you do the generative version. Okay, so now I'm going to start saying what happens when we lose information about our free surface height and try to make an inference. Let's see, how are we doing on time? Okay, doing well. So previously I showed essentially what was a full resolution image of the model. But now I'm going to start coarse graining the sea surface height from, well, what you see here to this more pixelated version, to more pixelated, to extremely pixelated, and ask the exact same question. How well can I predict the ocean's subsurface if this is the information that I'm providing? Intuitively, if you only give 4 values and you're trying to make a prediction at, let's say, 256 squared other values, you may expect to lose some information. And that is indeed the case. Again, I produce 100 samples and then I average them. And you just see going from the top where things are informative down to the bottom, the image is changing and becoming more washed out. And this is exactly a proxy for just saying that you're having even more samples of AI. You get a wider variety of samples when you lose information. And when you look at the standard deviation of your 100 ensemble members, you see that it increases as you decrease information. So you're becoming more and more certain about what you can, more and more uncertain about what you can predict when you coarse grain more and more the information that you have. This is a good sign. This is a sanity check. We expect when we use less information to be able to predict less. And well, indeed, the machine learning model does give that to you. And if you actually go to the very extreme where you only provide the sea surface height average, so you only provide one number, you can actually compare that to, well, what happens if I take my data set and I just take the time average of the entire data set? So the image on the left is what happens when I take the data that the neural network was trained on and I take a time average of all the zonal velocity fields. The AI mean is what I predict when I take my 100 ensemble members and I average them. And I get that. And they look very similar, maybe a little bit wavier for the AI mean. And I think that's just because I only drew 100 ensemble members. If I drew 1,000 or 10,000, I'd bet that it looked way more like that ocean simulation mean. In other words, it's an ensemble versus time average correspondence here. And if you look at the standard deviation from the data versus the AI standard deviation, they also look the same. In other words, this is exactly the case that I described before, where the conditional distribution is reducing to the marginal distribution. The information I'm providing is completely useless. If I take an ensemble mean, essentially this neural network is just reproducing the existing training data set. It's just drawing samples very similar to what it was trained on, without taking into account the free surface height at all. And similarly for the other fields as well. One thing to emphasize here is that even though making this correspondence between time averages and ensemble averages, the future is actually not is in a statistically stationary state. So the correspondence is a little iffy, but visually you see the similarity. But you can look at more than just these pointwise statistics. What generative AI methods are meant to do is capture all higher order statistics of whatever image that you're looking at. It's really supposed to capture this extremely high dimensional quantity. So the other thing that you can do is you can take various higher order statistics, and here I'm looking at a covariance corresponding to meridional heat transport. In other words, the amount of heat that's being transported at a given level of depth. This is a product of the vertical velocity and temperature fields, so you can already see that it's a higher order statistics because it's a product of things as opposed to just looking at the field itself. And then I'm also taking a horizontal average. So it also needs to look at the correlation between all the horizontal points, east-west points in this case. The blue line is what's given by the ocean simulation, and then the red band is the predictions from all the different ensemble members of the neural network. The main thing that you see is that there's a lot of purple, that basically the neural network is able to actually predict the heat flux very well. Except for that bottom right one, where you have more uncertainty as well. And that's also a good piece of information to have. That, okay, like maybe I'm not perfectly predicting the heat flux, but I know that it's within this plausible range. Again, a higher order statistic, so it's impressive that these models can even get things like this right. Because usually when you use generative models, let me just take a step back, you ask for, let's say, an image of a puppy, and it gives you a puppy, and you're like, ah, okay, good, I got a puppy, great. But for science, we want it to be quantitatively correct. It actually has to give us the right number within 10%. Like, I don't know what it means to get like 10% of a puppy right, but I do know what it means to get the heat transport right. And it's a similar thing when you coarse grain. So at the top, this is when you lose information. So starting from the left, you have the most amount of information, and from the right, you have the least. And you see these red bands just expand, meaning that you're becoming more uncertain about what you can predict as you lose information. And again, this is also replicated with the generative AI model. So far, I've only looked at things at a given slice, and you can also look at correlations across the vertical direction as well. So here, I'm showing the ocean simulation correlation with the ocean surface field. And this is just saying, okay, I take my top level field, I look at the Pearson correlation coefficient at every depth below, and I get these numbers for the different fields that I have. So both for the different velocity components, temperature, and, the different velocity components and temperature. I can also do the same thing with AI, where I would look at this correlation between what I infer for the surface and what I infer for the bottom. And you see that the structure is very similar to the original ocean simulation. Now, this is a slightly different thing that I'm measuring here. Here I'm looking at the correlation between the predicted field. So this is a Pearson correlation coefficient at every depth between what the AI model predicts and what the ocean simulation actually produced. So that's the middle one over there. So for the different fields, you see that the correlation coefficient are pretty much close to 1 for the velocity fields. And for the vertical velocity field, it's a little bit less. It's around 0.8. So that's the green line that you see. The last one is a different measure. I'm pretending that one of the ensemble members that I drew is, let's say, my perfect prediction, and I correlate my 99 other predictions from the neural network to that one that I'm holding out. And from there, you see a very similar structure from the ocean simulation. I'm using this as a proxy for the samples drawn from the generative AI model are similar to the actual observations that we would expect as a ground truth. Whenever you start doing probabilistic comparisons to things that you only have one value for, you have to start getting creative about how you actually make that comparison. And this is one way to say, okay, I have a distributional measure, but I'm only making one observation. How do I reconcile the fact that this sample member is actually similar to one of the samples I've seen before? This is one way. And you can also do this when you use way less information. So when you have this extremely coarse-grained sea surface height and you try to make a prediction. And for the sake of time, I also want to say that you can also look at integrated vertical velocity. So this is a quantity that oceanographers care about, especially physical oceanographers. basically it tells you what the total heat transport in the ocean is, and just saying like, yes, you can take into account correlations of vertical, horizontal, and get a reasonable estimate of what the zonally and vertically integrated meridional heat transport is. For our sake, it's just another higher order statistic to calculate. And you can also calculate yet another higher order statistic, such as the overturning circulation. So the main takeaway that I want everyone here to have is that really that all questions in science really should be formulated as probabilistic inference questions, because that is the more natural way to phrase questions. And the other one is that generative AI, although it's been used for image generation in the past, and we haven't, let's say, tried to be too quantitative about what it means for science, I hope to demonstrate that we really can start using it for science as long as we do a good job with the training. And we can ask questions that we really couldn't, well, we could ask them before, but we couldn't really address it. And in this case, it's how much does the ocean sea surface height constrain the ocean interior? For oceanographers, it's been known for a while that it actually provides a strong constraint. But this provides another way, at least in the context of the models that we produce, to see how much it does constrain the ocean interior. And with that, I welcome questions.
Thank you for a great talk. And I only have one question, which is, when you look at your generative AI results and you compare it with the standard approaches that people use in the field, how well do they compare? I mean, and if you have a ground truth, in the case that you actually know the exact value because you had some probe going there and actually measuring it, how well does it fit the actual data that you get? Thank you.
Yeah, so in order fitting, let's say, observational systems, that would be contingent on how well the model already does. So here, I'm thinking of this almost more like a theory type approach where in the past, for oceanography to do the same problem, they'd use something called essentially the quasi-geostrophic equations. Surface quasi-geostrophic equations would be the equivalent, where they take the free surface height information, they basically calculate a more sophisticated inverse Laplacian, and they predict what's happening in the ocean interior. And this instead says, okay, we don't need this analytic equation. We have a whole model that includes all the most sophisticated physics that we know. What if we do that same exercise of trying to predict what happens in the interior with that? So the success of this model with actual observations will be completely dependent on how well the ocean model does at making inferences. Now, let's say you use an ocean model that's already been calibrated to match statistics of the Earth system. I don't know. I've never actually tried it, but it would be interesting to try to see how well this does predict the ocean interior. I know that when people have tried the theory-based approaches, they've been very far off and be able to predict especially the vertical velocity, like by an order of magnitude in the ocean. And I'm hoping that something like this would get you, well, not an order of magnitude off, but something much closer than the previous theory approaches. Thank you. Mm-hmm.
Hey, thanks for this great talk, Andre. I have a question about what's the unit that you use.
Yep.
So if I'm not mistaken, you use 15 vertical levels in your ocean model.
Yes.
And do you implement the depth dimension as additional channels? Or is this a really truly 3D convolution?
In this case, I used a 2D unit. Okay. Yeah. So a 3D unit, I think, would make more sense if I had more vertical levels. But because I only had 15, a 2D unit included as extra channels, well, I think was perfectly fine. I think it would do better with the 3D unit, though.
Okay, that's interesting because everybody does it like this, even if you have higher resolution. So I'm just wondering if there is a theoretical reason why the vertical dimension might be really different than the horizontal dimension and better handled as channels, or is there it's just more convenient? I don't know.
I think it's because usually you have less vertical, like the number of degrees of freedom you have is way less in the vertical than the horizontal. So in the horizontal there I had 256 square degrees of freedom, and in the vertical I had 15. So that's a pretty big order of magnitude difference. And also because I have so few vertical levels, the field itself isn't as continuous as one would expect. So that inductive bias that you get of continuity from the 3D unit doesn't quite apply as well. Like the very top surface is discontinuous from the second level, for example.
Yeah, great presentation again. I'm wondering if you have thoughts about the atmosphere side of things. I've seen applications like this a little bit. I've seen some of your presentations before. I'm wondering if the same methods are applicable to the atmosphere. Has it been done? Do you think it's going to be done?
Yeah, so the approach is very general, right? It just says you have some model, you have something that you want to make an inference from. How far can you go? So to me, an interesting question that you can ask about the atmosphere that's essentially exactly the same question is the predictability question. So we have this time scale of about 2 weeks for atmospheric predictability that people have cited over and over again. But with this kind of method, you could be a bit more quantitative about exactly what that 2-week atmospheric predictability window is, given whatever state that you have. Here, it's not the ocean surface predicting ocean interior. It's the previous day's initial condition, and you want to make a prediction of the next day. So those are the two. Given information is what we know today, and the information that we want to predict is information tomorrow, or 2 days later, 3 days later, 4 days later, etc. And so that would be one equivalent of the atmospheric case. And I've seen people apply autoregressive generative models, but I haven't seen people try to ask this science question of what is the predictability window of this given model. The exact equivalent atmospheric question would be if you have surface pressure and you want to predict the entire atmospheric state, which is also very interesting too. But I haven't seen anyone do it.
So your setup was a double gyre, right? And
Yes.
I mean, arguably one could say like there's a specific region of interest in the ocean. And so you would say like, cool, for this region in the ocean, I only need surface measurements in order to infer what's happening below. But how much do you think this actually generalizes to different ocean regions, right? Because in double gyre is very much like wind-driven circulation. There's obviously many other places where you have very different dynamics at play. Could you, really think about, is there, or like even infer, like what has it exactly learned? Can you therefore only, let's say, I don't know, you were to look at I don't know, you didn't, but like, let's say you only like learned the barotropic dynamics, you can always infer this one, but you couldn't infer other dynamics and so on. So you can kind of assess what has it learned, much can it generalize to other regions?
Yeah, that's a great question. And it's something that like oceanographers can kind of done by hand in a way. Like Carl Wunsch is being the best example that I can think of. He has all these regions where he looks at in this region of the ocean, I don't expect stationarity because of all these things happening. So I don't expect the past to be very informative of the future of this particular region. And I'd say the main thing that, like, you would have to train on the different regions of the ocean because there are different dynamics. But it would be interesting on various respects either to say like, okay, these regions are similar enough to where I can use, let's say, the same latent space transformation to go between them, to use a machine learning terminology, or to just train on the entire global ocean and make inferences that way. And I think mentally the thing that I was thinking about for the future was to train on a full-scale ocean model, like the kind of simulations that Simone has shown, with a sea ice, some reanalysis data of the atmosphere, or even like a coupled climate model to try to do the same inference exactly for this reason that of the heterogeneity of the Earth. The different regions are just so different that I'm not sure that we can translate what I've learned here to other regions. It might be the case that in certain places the sea surface side is very informative, other places not. And that would be interesting to see. If there are no more questions, I'm happy to talk later, and I'll see you guys in the afternoon to learn about, well, how to actually do this denoising diffusion stuff.